Hello students of computer architecture. We're here today to solve a problem on direct map caching. And so we have two blocks of memory, our main memory and our cache. Memory has one word per cell, a 32-bit address, and 8 gigabytes of total memory. Our cache has 512 kilobytes of total cache and 64 bits per line. So, 64 bytes per line. So, we have been given a memory address, 000E602, and our first question is to find this address in base 10. Now this is quite simply done by first converting from hexadecimal to binary. Okay, once we've got it in binary, it's very easy to take 2 to the power of 1 plus 2 to the power of 10 plus 2 to the power of 11, 13. And when we've added all of these together, we will have our answer in base 10. With the magic of editing, we have converted all of these to the power of 2 numbers to their base 10 equivalent and added them together. What this means is that this number is the cell number that our memory address is contained at.
To answer the next couple of questions, it's going to help to know exactly what cache is. So cache is smaller than memory, and it's divided into words, which go from left to right, and lines, which go up, down, top to bottom. Because it's smaller than memory, multiple blocks from memory can be mapped to the same lines, which means that we have what we call a virtual address. And the virtual address is chunked into 3 parts. The first bits are the tag, the second set of bits are the line, and the last bit is the word. So what the word tells you is which word in the cache you're looking at. This tells you which line in the cache you're looking at, and tag kind of makes it clear which chunk of memory you're looking at, like which chunk of memory is loaded into the cache at any given time, because you could have multiple blocks that could be in any line. All right, so we're going to start by finding how many bits of the virtual address, which we know from the beginning is 32 bits altogether. We're going to find out how many of those bits are the tag bits. And the way we're going to find that out is because cache is smaller than memory, we have to figure out how many memories fit into cache at any one given time. So we're going to be dividing the amount of memory, like the bytes in memory, divided by the bytes in cache. So to figure that out, first of all, we're going to need to do 8 gigabytes. We know a gigabyte is equal to 2 to the 30 bytes, and 8 is 2 to the 3. We multiply those together, we get 8 gigabytes is equal to 2 to the 33 bytes. And we have 512 kilobytes of cache. We know that a kilobyte is 2 to the 10. 512 is 2 to the 9. Multiply those together, and we end up with 2 to the 19 bytes. And then to figure out how many memories fit into cache at any time, we've got 2 to the 33 divided by 2 to the 19, which equals 2 to the 14. Awesome. And when we look at that, we know that if there's 2 to the 14, we're going to take the log base 2 of that. 2 to the 14, that's 14. So we know that the tag is 14 bits of the address.
Okay, so now we need to find the line in our virtual address. So what we need to do is take the 512 kilobyte total cache and divide that by the 64 bytes per line. So we know the 512 kilobytes is 2 to the 19. And for 64 bytes, that is 2 to the 6. So if we divide these, we get 2 to the 13. And then we have to log this, so log 2 to the 13, and that will give us our line size. So the last thing we need to find is the word. It's pretty easy to do now that we have the tag and the line. All we need to take is the 32-bit address, minus 14 from it, and also minus 13 from it. And that will give us 5.
So we're going to take a step back and look at our original 32-bit address, which we converted from hex to binary. And now we know exactly how that address is split up into our virtual address. So the least significant 5 digits are going to go to word, and they're right here. That's going to be our word. And if we do a little bit of binary calculation, we're going to know that that's in word 2. And the next bits we're going to look at are the 13 that are dedicated to line, which is going to take us up to here. And if we do a little bit of calculation, which I'm not going to show you here, but you can do it at home, we'll get to 1840, and that's going to be the line we're in. And then all of these remaining zeros over here will be our tag, and they're just going to convert to 0. So we have our word 2, our line 1840, and our tag 0. Okay, so now we're going to imagine we're actually looking at cache, and we're going to find the address we're looking for. So we're going to start at word 0 here and count up to word 2, and we're going to go down here, and we're going to start at line 0 and count all the way down to line 1840, and we'll find that our address is located here at tag 0, which means that there's other possible addresses that could have been located here and blocked from memory as a block, but this is the 1, 0 that we're looking at. So that will answer our questions of what line it's in. It's in this line. It will answer our question of which word is in that line. It's in word 2. And it will answer our question of the tag, which is 0.
So after going through all of that wonderful calculation, we have A, which is 58882 cell number, and then it'll be 1840 for the line, word 2, and then the tag is 0. Since this is a direct map cache, the blocks line up perfectly with lines, so therefore our answer for D is also 1840. Now moving on, which other cells are also in the same block of memory? Since we figured out that the address is 58882, and we also know that the word is in word 2, it also means that there are 2 other words prior to word 2. And the line goes from 0 all the way to 31, and we're going from 58880, 58881, and then this is the word that we figured out earlier, right? And it goes all the way to 58911. And this is going to be your answer for F.